Hi, hello. How are you doing? How is the things going? How are the things? Hmm. Um, just a moment of technical sound check. Do you hear me? Is the sound good? Do you see the picture? Hmm. I think I prepared everything and it should work. All right. All right. Everything is done and the stream started. So, hello all. Today I am presenting another kind of a talk about type level OOP made in Haskell. This is a talk about some use cases you would like to mm, some use cases for top level programming in Haskell, and these use cases can justify the complexity that emerges from this kind of programming, because Haskell in this area is not an easy language, it's a difficult language. And why doing type level programming, right? And this talk is inspired by my recent activities. I finished the seventh chapter of my Pragmatic Type-Level Design book, so wanted to share with you my findings, and the topic might be interesting to those people who love type-level programming, although I understand that in Haskell pretty much every person, um, every Haskeller loves programming on types, on the type level, and knows a lot of things from there. And Haskellers typically love doing things very complicated, very mathy. This is not my concern. I wanted to provide some pragmatic framework, reasoning framework for type level programming, and demonstrate when it's okay to use it and when it's an overkill. Yeah, so hello again. I see some comments. Kan, sorry, Kantemir Malinovy. All right, hello. He is writing Granin. Yeah. Uh, I'm not sure. Please write into chat. Is everything okay? I'll watch. Let me listen the stream. Yeah. It says something. All right. So, all right. Let's start. The problem I was solving with this solution with type level object oriented programming mm, is my idea, my concept of a game. It's a roguelike game about some character that is driven by artificial intelligence, and this character explores the world full of different objects. This is a zero player roguelike game, meaning that the player the user doesn't control the character directly, but instead the user should affect the world, should affect the surroundings and change the world in a way that the character could learn and could progress through the objectives, through the goals. So this is a concept, and as usual for such a complex game as roguelike games, it's not an easy to develop the way the world should behave, because in roguelike games it's very important what mechanics is there. For example, NetHack games, or maybe Atom, or maybe even Dwarf Fortress, the mechanics of the world is the most important part of the game, not graphics, probably not story, because it's very difficult to make a story, but still it's possible, but not an easy task. So my considerations were like I need to uh, create some maybe ontology, some graph of things, so that the artificial intelligence and characters could uh, learn about the world. They could discover parts of the graph and do some reasoning. They could state some goals. They could uh, find solutions by traversing graphs of knowledge and maintaining their own graph of knowledge. So this was the idea. Of course, the game is not yet finished, and I don't think it will be, because it's a hell lot of work. But the concept is very interesting and I liked it. And also, this was an interesting playground for the type level approaches. I am writing a book, almost finished with the main material, so I decided to join Zeplrog. It's the how the game is called, and my type level research. I did a lot of brainstorming about the game. For example, you see some uh, graph of properties. Every item, every notion in this world should be explained, should be denoted by some property. This is a high level idea. Property, it can be anything. It can be position, hit points, it can be inventory, it can be goal, or maybe a character. Everything, pretty much everything can be a property. It was clear that I need to hard code some initial game and properties, because the game should start from something, but this graph should also evolve with time. And this means I will have I will have static and dynamic parts with with a clear separation between the two. Static parts are those that cannot be changed. Static properties, static initial values, for example, initial hit points for a character, static scripts maybe for a game, and etc. So many static predefined data can be and should be provided with the game. But then when you start the game, everything should work dynamically. The graph should change and adapt. The characters should obtain new properties, and something can be dropped from their inventory, for example, or can be found and put into the inventory. So those things should be dynamic. And this idea of having two worlds of static properties and dynamic properties evolved drastically into a whole concept of ontology for game. So the idea was that I should be able to navigate across the graph, to make queries to the graph using some regular language similar to regexp maybe, so that it could be possible to address any portion of the graph and probably change something. This means I also need a scripting language for that. Not only properties, static or dynamic, but also some scripting possibilities. And yes, I decided to make everything on the type level. That's a very responsible decision, because in other under other circumstances I would avoid doing something on the level of types. It's too much complexity, and doing this with bar values, bar types, regular types, not type level types, is a more common and more feasible approach, but I didn't look for easy ways. So this led me to some uh, approaches, tricks that I used all across the book, and those approaches and tricks helped me to build some interesting uh, data model of this graph. Let me show you a specific part of an example graph. This is a property that's called specific door, and there is a property that's called abstract door. Here we see the OOP idea. There are some abstract notions, and there are specific notions that derive properties and other items from abstract notions. Why this is needed? Well, because in roguelike games you have, for example, a door on the map, but this door is not the only door available in this game. There are many doors, and most of them are alike. They are similar. So you don't really want to program each door separately, right? You need to have some template and instantiate that template many times. But sometimes you need a specific door instead of a regular door. This specific door can be, for example, hidden, or can be locked, or will have some other possibilities and properties that a regular door doesn't have. So the OOP idea with inheritance comes naturally from this consideration. It's not the only way to encode such an relation. When you have a common door and abstract door and some secret door, there are other ways for sure, but this was the task for me. And after some development, we can describe graphs like this. This is a static plus dynamic graph. Dynamic graph nodes, meaning properties, are represented with this hashtag without a circle, and static are represented with those circles. And there are some values that can be properties, but actually they would be better values, because I can have children properties with a single value, but also the model allows me to skip the step and instead of these properties use values directly. But that's a tiny detail. So there is a static part and there is a dynamic part. Well, actually, it's not even the whole story. Well, this is a schematic representation of inheritance. There is an abstract lamp, there is a specific lamp, and they both have a bool value, meaning that the abstract lamp declares it should have boolean value named EA is on, and a simple lamp will derive this value from abstract lamp and will have this field too. So it's possible to derive fields, properties, even scripts. And the chain of inheritance can be long. It's not restricted. So you can have, for example, two intermediate abstract properties having own values or something. Well, this is where you analyze your domain, and if you see it requires that, all right, sure, why not? Yes, I know, in object-oriented programming, long inheritance chains are not very appreciated, and this is a good idea to not appreciate them, because long inheritance chains are fragile, and in general it's a bad design approach. Well, I left this possibility. You don't have to use this, but it can be useful in some cases. So yes, I did this. There are even more ways to group properties and to make them connected somehow in this model. For example, every property will belong to some group. In this case, the concrete property 1 belongs to group through the chain of abstract properties, the top of which belongs to the group. And there is another concrete property that also belongs to this group through own chain of properties. This is a way to group properties and probably query something. If you have a specific group, you can query those properties that belong to this group. This helps to discover new things in the graph. It needed for the query language. This is another picture about grouping. And also properties can reference each other. For example, the group 2 can reference another concrete property and therefore connect to another part of the graph. This can be used to make distant relations between various properties and may be required by the domain. I said there is a static model and dynamic model. This is true, but not the whole truth, because static can be type level, this to the left, and can be value level. Static type level is what we are writing in our editor. All those types, exclusively types, and values are not types, and when you do static materialization you will get a value level model. It won't be dynamic, meaning that it cannot change. It will be just a representation of type level model made on value level, because we need to keep our initial graph for documentation purposes and for querying purposes, but this part vanishes after compilation, because compilation erases types, right? We still need this part of what were the static properties that were used to create dynamic properties. So after static materialization you get this value level model, and it remains I'm not sure, intact. What is the correct word for that? It remains in your program unchanged, and then you use it to instantiate dynamic properties on the fly. This is where it looks like OOP instantiation, and you can do a lot of things on the dynamic instantiation. Yes, this is the concept, the idea, and the description of the OOP model, and the question is how to hello. Hello. Unfortunately, my OBS has crashed again. This happens when I switch between windows, and that's not a good sign. I could not fix it yet. Sorry for that. So let's talk about the code. I won't dive too deep into this code because it requires some Haskell knowledge and some preparation, because the project is very big. But I want to share some points that type level programming in Haskell doesn't have to be complex. It doesn't have to be mind-blowing or mathy. You will typically not see a code like this in any Haskell project, because in Haskell projects, in libraries, for example, the type level programming is too abstract, too mathy, too detached from real tasks, and also unordered in the sense that there is no unifying principle under that programming. Every person does it differently without any design or idea behind. My type level programming approach means creating understandable and good in usage domain specific languages, mostly interpretable languages, but it's not the strict requirement, just languages. And using those languages, you can really achieve a lot of stuff. You don't have to program generically, but to make this happen, certainly several tricks should be used and adopted. Let's try to learn what is written here. So this is a type. Everything you see here is a type. It's not a value, although may look like a value. It's everything is type. For example, this is a list of something, type level list of something, and this is another list of something. Again, it's a type. Any prop is a property, abstract property that belongs to the group AnyProp and doesn't have fields. This one is fields and doesn't have scripts, but it's a type. It's type made from abstract prop, and this is abstract derived prop that references any prop as a parent, as an abstract parent. It has own identifier. Those identifiers are just strings. For example, let me show you the AnyProp identifier. It's just a string. Well, just a string. It's a type level string. Type level strings are they look similar in Haskell like ordinary strings, but they are not string. They are symbol. So this is not the whole truth, but still this is not a string, it's symbol. And ESS, it's a shorthand for essence. This is a type that denotes some identifier. I called it essence. I could call it identifier or maybe ID or something like that, or key, but I decided to call it essence for some reason. Well, yes, it's a type level string wrapped into essence type. And to specifically denote that it's a type level feature, I use that so-called granular type selector design pattern. You won't find this design pattern anywhere because I invented it. So I use it to separate type level and value level, and I'll show you how it works. But let's just look at this thing as a key, as an identifier for our bits, because every property should have either name or key, and properties can have fields. Those fields should have names, this time not just names but essences. And this structure, this list, represents a key value dictionary for properties. This key value dictionary is the same idea like in Python. In Python you have a class and fields. Class is essentially a dictionary of fields that you can access using some key. Well, it's the same idea. So, I think Python is not the only language with this idea. Maybe Clojure as well. It's a dynamic way of defining fields. In my case, those are field names, for example, icon, and this is a value of this field. Uh, it's a simple value, icon val, and icon val is my custom type, and it gets a string as a parameter. So icon val is also a type, right? Let's take a look. Yes, icon val is just a string value type. This is my internal machinery to denote some type. String value icon. It's a type of string. And the other fields do something else, right? They are values in this case, and in this case it's not just a key value, it's a key back, meaning that there is a key and there is a list of different items, not only value or something like that. You can have references here, or you can have child properties here, but I also can combine different stuff using keyback, this approach. So this is how you define your objects, and then you can derive specific classes in quotes, specific classes from this object. For example, a specific door. It can redefine and override the fields, or it can get fields from the abstract parent. There is no script, it's an empty list of scripts, but it will get one from here. This script allows me to do a lot of stuff, at least in its idea, a lot of stuff with this property, or maybe with the rest of the graph using those connections. We can move from this property to any prop using some query language, or maybe we can submerge to the referenced properties and do stuff. Every script can be seen as a method, like every class can have a method, right? And every property can have own scripts, but they are not quite methods, and they are something more general. They could serve as a methods. The question is, what we'll call those methods? Well, in my game there are even more domain notions such as effects and events, and they can call those scripts from different properties. At the moment, this script is very simple. It is a script. Again, it's a type. It has name. It has only one instruction to write some data to the field eState. This is a list of essences that points to some field from a constant. This constant is this reference or list of essences. So it will replace what is found like here with some content from here. We can take a look what is the eState. There is a field eState. It's a value, and this value will be replaced with something else. This is an open door script, so this reference will be replaced with this reference, and those references also work like relative links to some internals of the property. This one points to eState close. Let's take a look. So we have this property, and there is eState, and it points to eStates, and points to eState close. It points to here. So naturally, this is an enumeration of possible states, and we can reference any possible state from here and change it with script. This is the whole idea. of type level properties, and this property will be compiled into static value level property of the same structure, and then when needed it can be instantiated into specific dynamic doors. And I can add properties on the fly, I can remove properties on the fly, I can change values on the fly, I can even change and update scripts if I want to. It's not implemented, but I can add new scripts, I can remove scripts, I can merge different scripts if I need to. So this means it's possible to have arbitrary data with arbitrary methods. Yeah, this will be not an easy task to implement for the game, because a game is typically very big, but still. Let's take a look at the models, at the actual models behind those notions. There are two models, well, two kinds of models, static and dynamic. Static model, for example, common. As I said, essence is an ID of some item. It can be key, it can be name, and I use granular type selector design pattern here. This is a type parameter. I see some comment. Alexander Shestakov says, can you amend script in runtime after this thing is compiled? Yes, I can. It's not yet implemented, but scripts are pretty much values, so they can be changed and rewritten completely. For example, you can add new instructions into this list of instructions. You can replace the instructions with something else. The scripting possibilities are not yet rich, and there is a limited set of instructions here. But yes, you can. The question is, what exactly scripting possibilities we need? You cannot do much on the level of types. You cannot have arbitrary types, because everything should be encoded, right? And for example, there is an integer type level type, there is boolean type level type, and there is string type level type, but they are different from value level types. Let me explain. And this is about the granular type selector design pattern. So this is a regular algebraic data type with some type parameter. This is an extra type parameter that communicates what level we address, either it's a type level or a value level, and the representation of this type will be different. In Haskell, when you declared ADT like this, you will have ASS as a value, right? You can write, for example, my val ESS blah blah. This is a value. This is a simple value of something. Let me simplify the type for essence. Let's call it x string to essence x. Just a simple algebraic data type. Right? But you can notice I don't do that. I create types. It's another level of working with. Compare this. There is a type, not a value. This is also a type, and some type mark is passed here, and this is also a type. We can consider type level strings as types. pretty much as integers as types. So this is a value and this is a type, and this is a type. We see here not a type, it's a value. Right here it's a value constructor, and this one is that thing, but it's not value anymore. You can lift value constructors to be types using data kinds extension. Once this extension is used, all the algebraic data types will serve like templates for some hidden redefinings. There will be some ESS, which is now a type. It's now a type, and it will have a kind of essence. This is promoted to types. This is promoted to so-called kinds, even more high, even a higher level. So this is what data kinds do, and those bits will be here in your module. You don't see it, but they will be here. This is a pseudocode for sure. And let me show you a picture. I guess the OBS can. All right, seems OBS is working, right? Yes, it works. So you can promote algebraic data types to be types and kinds. So if you had a Boolean algebraic data type, it becomes a Boolean kind. If you have had a true and false value constructors, they become true and false types with this apostrophe in front of them. And this is a separate model. It will be generated implicitly for you, and using this model you can work with the notions as types. So what I do in my code, this is a complication for sure, because I wish to see those things that like they are promoted and have them more explicit, but we cannot see them here. So this is a regular algebraic data type and regular value, but this one will be promoted and we can use it on the level of types. Well, as long as we have it in the same module, it will be promoted too, and we will have more type level bits from this ADT as well. But the point is, we need to distinguish between type level and value level. This is one tricky idea. Another tricky idea is that I deleted for another tricky idea is that string is only a value level type. It cannot be a type level string, because string is not supposed to be a type level string. There is another specific type in Haskell. It's called symbol. This one can be promoted to the type level and can be filled with values, with type level values like this. So we either have a string or a symbol. This one for type level and this one for value level only. So how can we do that? We want to have a model that will work both on the type level and on the value level, because when I compile type level representations, these ones, I want to put them into the same model. I don't want to write a lot of boilerplate. I can compile those things into separate model, and I will have the whole folder of those models and the separate types for value level static model. This would be very tedious to do, too much things to think about. So I can reuse the same types because I already have them. I can reuse them for static type level and static value level models. But there is a problem. I should have either symbol or string instead of field. I cannot have both. I cannot do string with type level and vice versa. So this is where I use granular type selector design pattern. I say it will be a string, it will be some string type, but this string type should be selected by the compiler depending on what I pass here. If it's a type level, then it will be a symbol. If it's a value level, then it will be a string. And this design pattern works like here. Let me open the design pattern, and I see some comment from Alexander Shostakov. So this level is mentioned in some type family to switch representations. Can you address this part, please? Looks interesting. Oh, clear now. Same JDT for both types and values. Cool. Yes. This is what I want to share. Type selector design pattern. It's called granular because there is one more. There is one more design pattern type selector which is not granular and has a different structure. Also, I describe in another book. So there is a specific selector for type or value level, and yes, it defines exactly what type will be substituted. So if we then yes, there is this type family, which is another mind-blowing Haskell feature because we actually have 4 different type families, if not more, and this one is very simple. So this type family, actually, it's a table. It tries to look at the mark and substitute itself with either symbol or string. So if it's type level, it substitutes with symbol, and value level is string. Same story for integers. There is a not type for type level. Things also can work on the value level, but I prefer to not do. And there is int for value level stuff. And yes, this is a type family that selects a specific field type on the compilation. So we can alter our algebraic data types. We can alter the types of the fields. We actually can alter the fields completely. It can be a very complicated compound type instead of string. It can be a pair, a list of something. It can be another nested algebraic data type. So altering fields in Haskell is possible, and the granular type selector is a variation of higher kind of data design pattern, allows us to select types for fields. You can see I push this value, this type parameter to every structure. This is a very I would say boilerplate solution, but it works, and probably it's not that difficult. Every possible type has it. What's more interesting that I have some algebraic data types which, yes, they can be used both for static type level model and static value level model, but sometimes I need to make them very different. This is two variants for static type level representation. This is shorthand for type level, and actually it's a shortcut for type level parameter. I can write it here. And this one is used for value level. In this case, it's a generalized data type, a generalized algebraic data type, and you cannot reference group and group root on the value level because it won't compile. It says it should be type level, and all the things here are type level and cannot have value level representation. So it's literally impossible to create values of those value constructors. Those are only for value for a type level, and those are only for a value level. So you cannot create types from those things. Well, actually, Haskell generates some types, but they are unusable, and the JDT feature looks at the returning type of those value constructors and doesn't allow to mix the levels. So this is how I achieve some, well, type safety essentially, but it's used for distinguishing between different models, because on the type level I don't have static property ID yet. It will occur only when I compile type level model into value level model, and I have to keep it. So it is another field that occurs here. Alexander Shostakov writes, but pattern match exhaustive check will help you if you mix and value at same JDT. Even better, the type checker understands that I cannot create values of those things, and it doesn't say they are missing, and it only requires those two. Alexander пишет yell instead of help. I didn't get it. Sorry. So the type checker is very smart, and it sees that only those value constructors should be pattern matched. This is very convenient because I don't need to pattern match everything. It's literally impossible to pattern match on those things. Yeah. How to complete misfired, says Alexander. Oh, nice, says he. Yeah. For example, I have some pattern matching here in the instantiation of a script. Correct? I believe so. Maybe. Or maybe instantiation of property. I want to demonstrate this. Predict. Yes, I can demonstrate on this basis. It's an instantiator, meaning it creates value level dynamic properties and other stuff. So I pattern match on tag propref and on predict. Those two can occur on the value level. But let's look at the actual data type. The actual data type for property contains tag propref. It can be used on both levels because LVL is not specified. Can be both. It also has derived prop, but it's only for type level, and all those fields are also type level. And predict only for value level. Again, the type checker will understand that, and it doesn't require to match against all other value constructors here. This is very good. I'm not sure if it works in other languages. For example, Akamel has JDTs. I'm still exploring its type level possibilities, but this time it works very nice. Yeah. So this is how I define it. Very, very dense material. And there are two stages of compilation. First is materialization, static materialization. Let me just show you some high level stuff. there is a type class. Everything you do with types, you can only pattern on them and can transform them. Pattern matching on them can be done with type classes in Haskell. So there is a specific type class, smart, from materialization. It takes some initial type to pattern match and the result, and there is a payload here. It's again another design pattern. I call it dynamic payload. Initially you pattern match over types here in here uh, in here, and payload can be used to pass some extra info. As long as a type of some kind, you can only have a proxy for it. There is no value for such a type. So when you pattern match over the structure, every possible notion will be passed into the type class and we will be treated as a type, and this type should be connected to some other things. In my case, I convert types into regular value level ADTs. I can show you. I can show you, for example, for essence. This is a very boilerplate code, but it is what it is. So we have a materializer. Dynamic payload is empty, nothing to pass here. There is S, it's a type because it's promoted. This tick means it's promoted, it's a type. It's not a value constructor, it's a type. Also, we ensure it's a type using this mark because S is a parameterized thing. When it's promoted, its fields become type parameters. So S will have some type parameter, one of symbol, because this becomes symbol, and it will be of a kind essence. So if you have several fields, they all will be type parameters. And here this type parameter is filled with some string, type level string, and I should convert this type level string symbol into value level string. And this symbol has some machinery in Haskell. You can ask for a related string from it using symbol val, using this type class, and this will convert this type into just value. And then I create a value of the essence. It's a regular value, and return this regular value. So I had a type, now I have a value. I do this for the whole type level representation, and the code in this file is very typical. It can be generated. With template Haskell or maybe generics. I prefer to make it manually, but it's a very boilerplate code. And then I can instantiate my properties. Once I have static value level model, I can instantiate it into dynamic ones. This is a little bit more busy code because I need to carefully how to say, create links, create some instances, some IDs, but after first stage of static materialization happens, those abstract things go away. It's no longer an abstract thing. It's a specific property fully ready to be instantiated. So OOP happens on the static materialization phase, on the first phase, and then I can work with specific static properties from here. So OOP ends here, and usual programming starts here. Well, this is actually The idea is certainly much deeper than that, but requires a little bit more involvement. And for example, this is how type promotion looks like. I have a property data type. It's actually a mm, template, so I denoted it with this picture. It has value constructor and value and another value constructor, and the two of them can be promoted. This one will be promoted too, but we don't know how to use the stuff on the right. So I prefer to think that this is only a value level bit and cannot be promoted, cannot be pattern matched on the type level, and vice versa. This is only a type level thing and cannot be pattern matched on the value level. So that's it probably. Do you have questions? Do you like type level programming in Haskell? Maybe you would like to do that differently. For sure, I explain things better in my book, and it's a lot of stuff that is missing here. What are those type level symbols and natural values? How to deal with them? How to do static materialization, some other design patterns, and etc. and etc. A lot of stuff. More extensions from Haskell. Yeah, Alexander Shostakov writes, I very like the phrase, and here is the place where OP stops and real programming begins. All right, all right. All right. So that's it for today, right? I think we can finish probably. Yeah. So thank you for your attention and see you next time. Bye. Alexander says, so the whole idea is to do inheritance on typed baked then in on I don't see the word materialization phase and then use regular values. Yes, yes, it's the whole idea to have OOP on the level of types to make this inheritance. Well, I forgot to mention that I get some type safety from that. I can do scripting, and the scripting is type safe in some sense. There are fields, there are constants, and they should they should match on types they work on. This is not the whole story. So scripting is another topic to discuss, but it's too big to be addressed. So scripting is a very difficult topic, and yet not completely finished. So yeah, a lot of stuff here. Mm. Михаил is writing «Здорово, а чё на английском?» I'm translating «Hello, why English?» Well, just because I'm trying to address the English world with my materials, it will be better for me to present my talks on English to attract more attention from the English crowd. And maybe I have a plan to make more talks in English, but maybe I should create a separate channel for that. Yes, I know there should be a specific strategy for a channel if a person wants to be a blogger. I don't want to be a blogger right now, and probably don't want to develop my channels to the extent I can call myself a blogger. So this is why I have a mixed content. But if taken seriously, it should be a separate channel. Maybe I'll download all those videos and upload into a new channel as episodes. Yeah. Well, that's it. Let's finish. Let's finish today. Thank you and see you next time.